I'm a big fan of maps, both in real life and in fantasy. I'm also a big fan of so-called map games, where you try to take control of territory and manage vast swaths of land. So for a long time, I've been interested in making this kind of maps for games or stories, but I'm not a very talented artist. However, I do have a computer science degree, which tends to be more useful than my linguistics one. So instead of going through the long and arduous process of becoming a good artist or whatever, let's figure out how to use math to algorithmically make maps for us.
I think it's a sign of strength.
So an easy place to start is to generate some random values with the computer, and then assign those as heights. We can add more points to start getting a terrain-like variety, but it's way too blocky. So let's reduce it down to just 4. Instead, we can look at each pair of points and use algebra to get the line that connects them. Then when we draw that, the shape is a lot less blocky. We can then go a step further by using calculus to find an equation that has a continuous derivative, which will make our line have a nice round shape instead of sharp edges. Now this looks nice, but I think it's a lot simpler than what we would want for terrain. So we're going to use fractals to add some more complexity. Fractals are mathematical shapes that get more detailed the closer you zoom in. Fractals show up all over in math and science, but describing maps is actually one of the original reasons they were defined. Computers can easily make fractals by repeatedly applying some geometric rules. Like in this case, we take a straight line and repeatedly bend it. By doing this a number of times in a row, we can end up with a really complicated shape, even though the actual rules for making that were pretty simple. Fractals like this are perfectly self-similar fractals, but you can use a lot of the same concepts for less rigidly defined ones as well. In fact, to talk about the fractals I want to use in this video, I want to do a quick tangent to explain some music theory stuff. So sound is just an oscillating pattern of high and low air density. And when we play a note, we can record it in a waveform that shows the density visually like this. So this shape is the note A. But then I can add a distortion pedal to this electric guitar, and now an A sounds like this. And the waveform looks like this. By zooming in on the waveforms of both, we can see that the reason it's still an A is that the peaks and valleys are still the same. You can still make out high points on the distorted waveform, even though the low points are a lot more garbled. The frequency of these most obvious peaks is called the fundamental frequency of the sound, and it doesn't change even when we add distortion. What does change is the oscillations that happen in between these major peaks, which are called the partials of the sound. So we can think of the fundamental frequency as a overriding sine wave that gives the pitch, and then we can think of the partials as a series of smaller sine waves that add on to the original fundamental frequency. When we add partials like this, we can still tell what the base original pitch was, but now it has a lot more complicated, interesting sound. So going back to our terrain, we can view our original shape as something like the fundamental frequency, and then we can add something similar to partials by sampling points at twice the frequency as our original one. We can then repeat this as many times as we like, subdividing it each time in a fractal sort of manner, and end up with a really complicated shape that still maintains the character of our original base shape. And one of the cool things about this approach is that it all works just as well in higher dimensions. So instead of sampling points in one dimension, we can sample a 2D grid of points. Here we can slide our line along this new dimension to get some concept of the overall shape. But now that we're using 2-dimensional sample points, it's much more useful to visualize the results in 3 dimensions. We can also color the shape based on the height at that position. And then when we re-add the multiple octaves, it makes it really easy to see the texture that we've created. In general, this process we used is called fractal noise, and picking random values at specific points like this is called value noise. There's a lot of similar techniques that are either computationally faster or have slightly different resulting shapes, like Perlin noise and simplex noise. But the general concept of stacking these 2-dimensional waveforms on top of each other is pretty consistent. From here, it's pretty easy to add a water level, where any value below a certain point becomes a solid color, and get some pretty convincing looking maps. Because this is all computer generated, it's really easy to get as many versions of the same concept as we want. And we can change the scale by simply increasing or decreasing the amount of original reference points we start with. And for a lot of applications, this is good enough as it is. This really zoomed out map has a lot in common with the map you get when you zoom out the terrain for Minecraft. And if we zoom in slightly to have some more blobby terrain, we can get something reminiscent of big continents that we might see in a game like Civilization VI. Although, when trying to represent a whole globe like this, our generated map has a new problem. It doesn't wrap in a way that a globe should. If you look at this Civ 6 map, the right side matches the left side. But actually, when you think about it, that's not how globes work either. If we project that map onto a sphere, you'll see that near the poles it gets stretched out and looks really bad. Most maps work by having right-left be longitude and up-down be latitude. But when you draw latitude and longitude on a sphere, you can see why a flat map won't work very well. We can draw lines of equal latitude both near the pole and farther away. And on the flat map, these look like the same distance. But on the sphere, it's clear that the pink line should be much, much shorter. Only 38% of the size by my math. And so really, if we want to have an accurate map, we're going to have to work in 3D. Maps in 3D are always more difficult, because while ideally you'd have flat surfaces that you can draw on, you can't do that on a sphere without having some distortion or weird tiling. Like this globe from the Miraicon in Tokyo has to do this funky tiling to make squares approximate a round shape. The largest shape you can get without this problem is the icosahedron, which is the shape that a 20-sided dice uses. It's composed of 20 equilateral triangles that are all uniformly spaced around it. And interestingly, if you take the midpoints of those triangles and connect them instead, you get the second largest even tiling, a dodecahedron, or D12. This is called taking a dual of the shape, and we're going to use that more in a bit here. But back to the icosahedron. As I was saying, the icosahedron is the largest you can get while still having evenly sized faces. So if we want more than 20 faces, which we do for a detailed map, we're going to need to subdivide it somehow. And once again, we can look to fractals to do this really easily. We can take the midpoints of each side of a triangle and connect them together to make 4 new triangles. We can then use the same process on each of those triangles and repeat it as many times as we want. This process of subdividing the faces then has a really interesting effect on the dual of our shape that we talked about earlier. When we split our triangle into 4 triangles, the dual then has each of its pentagons connected with a hexagon. And when we subdivide our triangles, we add 2 more intervening hexagons. By subdividing our original triangle more and more, the dual can have an increasing amount of hexagons. So by the end, you have a sphere that mainly looks like it's tiled with hexagons, though you still will have 12 pentagons where the original icosahedron's points were. Because of this, nearly every time you see a globe shape made out of hexagons, if you look closely, you'll eventually find 12 pentagons hiding within it. To make the pentagons stand out less, we can also apply some distortion to the original triangles to make some more organic-looking shapes at the end result. Here we end up with a nice mix of hexagons, pentagons, and heptagons, which still work together to fully tile the sphere. Now that we have our 3D globe shape, we want to re-add our fractal noise. Though now it's gotten a little more complicated. In our first version of fractal noise, we inputted a position along the line, and outputted a height at that position. So to display the noise, we used a 2D graph. We then expanded it to take in both a x and y coordinate, and then outputted a height there. So we need to use a 3-dimensional graph to visualize the 2 input dimensions and 1 output dimension. But now, for our 3D globe, we're trying to input 3 dimensions and then see the height at that position in 3D. So we're going to need some way to visualize the 4th dimension. And the easiest way to do this is to extend some concepts we were already using to visualize the 3rd dimension. One thing we did earlier is to use a 2D image with color to represent the 3rd dimension. And then another thing we did was use a 2D image that we changed over time, sort of replacing a spatial dimension with a temporal one. So we can combine both of these to have a colored 2D grid that changes over time to get different slices of a 4th dimension. We can combine all those slices together to get a 3D volume, but then we can't really see anything other than the outside shell. From here, we can do something analogous to the water level we used in 3D. So we can set some threshold value and only draw the points that we evaluate to be above that value. This lets us visualize part of the volume in 3D while still not obscuring all of the internal structure. So the end result of all that is just a nice noise function we can use on our globe. It looks like it's wrapping nicely on the curved surface, but what's really going on is this is a thin slice of a 4D visualization of noise. And we can nicely visualize each layer of noise acting on a bigger or smaller region of the globe. By adding some colors and a nice water level, we can get some pretty good looking continents that don't have the issue we had with our flat map where the poles are all messed up. Once again, we're at a spot that's good enough for lots of applications, and we could stop here. But I have a nitpick that kind of bothers me about these purely noise-based terrain generation systems. Like, let's look at my copy of The Hobbit, which is of course in the canonical Japanese. This map has a feature that the ones we're generating can never have. Mountain ranges. In real life, mountains form lines based on plate tectonics, but with our method of randomly assigning heights to a grid of points, the odds of it lining up like that are very, very low. So let's try a new method that more closely aligns with how plate tectonics work. At the most basic level, plate tectonics says that the Earth crust is separated into two separate types, one that's a lot thicker than the other, and there's a big gap between the thickness of the two types. So to simulate this most basic idea of what plates are, we're going to take a bunch of sample points throughout our globe and then expand them randomly until we've divided the Earth into a bunch of organic-looking, semi-random plates. From here, we can look at each plate and randomly decide whether it's oceanic or continental. I'm going to base this off of Earth proportions and make it around 60% oceanic. Then, to simulate mountain ranges, we're going to need to assign each plate a direction of motion and speed. Motion around a sphere is kind of complicated, but luckily Euler figured it out in 1775. This theorem says that any motion on a sphere can be represented by a single 3D vector. So by assigning each of our plates a vector, we can use right-hand rule to see how that visualizes a rotation. And by using the cross product of that axis of rotation and the position of a particular part of our plate, we can get the motion at individual regions of the plate instead of just the whole one. Sorry for the sudden linear algebra, there's other places to learn what that means if you don't know. Essentially, this works out so that most plates are moving in a singular direction on the globe, but if the axis goes through the plate, then each point on it is moving in a different direction as the whole thing is rotating. The coloring you're seeing here is based on stress on individual tiles, which you can calculate by looking at the rotation of each tile and comparing it to the rotation of its neighbors. Here these tiles are yellow because neighbors have motions that are opposite of each other. Here you can see the lines pointing in different directions. Meanwhile, over here on the globe, it's a dark purple color because the motion of the individual tiles is moving away from their neighbors. By taking areas where the plates are moving together and raising the terrain, and then areas where the plates are moving apart and lowering it, we can end up creating a nice height map from that. And this has a lot of features we're missing with our noise-based method, like mountain ranges and island chains. In general, I really like how this looks, though it has its own issues as well. We need to have pretty big plates in order to have continent-like features, but because of that we end up with the internals of plates looking pretty flat. But thankfully, all that work we did to make a noise-based map can come in handy here. If we treat our tectonic simulation as the first couple layers of noise, and just layer in the higher octave, smaller impact noise, we can nicely texture our initial tectonic simulation. And this is honestly a nice analog to real life. Real life terrain is fractal, but not because it's totally self-similar. The geological and climate events that make things like the oceans are very different from the geological and climate events that make things like the Great Lakes. Just like with our approach here, where the big continents and oceans are formed from our tectonic simulation and the fine detail is from our noise algorithm. And I think this is where I'm happy to leave our map, at least for today. There's plenty of other things we can do. We barely simulated tectonics at all here, but I think it both looks pretty nice and has gotten me to learn a lot of cool stuff along the way. If you found this video interesting, I highly recommend checking out the YouTube channel Artifexian, who has a lot of great videos on making maps by hand and has some nice linguistic stuff as well. Some of the geometry in this video was inspired by the work of Andy Gainey, who has a channel here on YouTube, but also made a series of really good blog posts that unfortunately I gotta use the Internet Archive to find these days. Thanks for watching. I set up a Patreon if you want to support these videos financially. I plan on doing some behind-the-scenes stuff and live stream Q&As if you want to know how these videos are made, or if you just want to feel cool by being in video credits. And of course, feel free to not do any of that and keep watching these videos for free. I'm still just really excited that anyone's interested in the weird stuff I have to talk about. So again, I'll say, genuinely, thanks for watching. I'll be back with some more videos soon.